Differentials. If you have a graph of y against x, and they say y is a function of x, we pick 2 points here, and we call that y0, and that is y plus delta y. That means that distance from there to there is delta y. This is x0, and the point here is x0 plus delta x. That's point x1. And the y1, y0 plus delta y. This curve, we can find the gradient of that curve, and that gradient is changing y from there to there, which is delta y, over changing x, delta x. So we can write that, and for the same change, the delta y is the increase in y along the curve, the increase in y along that curve from there to there. And we're going to do a tangential to this point here, and that tangent will have a gradient. We want to bring this gradient down to that point to meet that tangential point here. So the dy is the increase in y along the tangent. They both have the same. For the dy, it has dx, and for the delta y also has delta x. And so we can write the gradient to be the change in y, the y naught, the bigger y, or the bigger y value. So y naught plus delta y. Take away the y naught, and we divide that by change in x, which is x naught plus delta x minus x naught. And you can see that the y naught, we cancel the y naught, because that's plus y naught minus y naught. X naught, we cancel the x naught, and we're left with the change in y over change in x. In the limit, when we bring this down close to the tangent, that's what we meant by in the limit, whereby the change in delta x gets smaller, and as it approaches 0, that's what we meant by that. As we bring it down close to that tangent, we then get dy dx. In the limit, delta y over delta x becomes dy dx. And we can also find dy dx, the gradient of a tangent, hence the word tangent here. The angle here, the angle tan of theta, will be equal to the change in y, dy, over dx. Tan theta will be equal to dy, change in y, over dx, change in x. And just to put that, this is y function, and so that gradient, that angle is this angle theta there. That's what we're talking about. And so that's the differential here. Differential is just finding the gradient of a function z, which is a function of x and y, and z plus change in z can be written as x plus change in x and y plus change in y, because I'm changing x and y. So I'll just put it there because I put that change in there. And therefore, if I move that z to the right, or take away z from both sides, but z is a function of x and y, so I can put it there in that equation there. And what I can do now is expand this function, and if I expand that function in terms of delta z and y, we will get delta z equals to a delta x plus b delta y. What that meant is we're writing it in terms of we're collecting all the delta x terms and all the delta y terms, and we would have a mix of delta x and y, where a and b are functions of x and y. And if y remains constant, delta y will be 0 because it doesn't change because it's constant. And if that's 0, then this will be 0. And delta z will be equal to a delta x plus higher powers of delta x, and therefore delta z over delta x will be approximately equal to a, because the higher powers of delta x will be small as delta x is small. And if delta x tend to 0, then a will be equal to partial derivative of z with respect to x. Partial because we're keeping y constant. So we're partially differentiating. We're keeping y constant. Similarly, if x remain constant, that is delta x equal to 0, then delta z will be equal to b delta y plus the higher power of delta y. Divide both sides by delta y. This will be 0 because higher power of delta y will be so small. We get delta z over delta y approximate to b. And therefore, if delta y tend to 0, we then get b to be equal to partial derivative of z with respect to y. Therefore, delta z will be equal to, remember that was a, and a is partial derivative of z with respect to x times delta x plus b delta y, and b is partial derivative of z with respect to y, plus the higher powers of small quantities. And then we can simplify by writing that to be just this, because those will be small. And then we can write it in terms of differentials. So if z is a function of x and y, we can write dz to be partial derivative of z with respect to x times dx plus partial derivative of z with respect to y times dy. We can also write this for a 3-dimension. We just incorporate the third dimension there, or 4 dimension or 5 dimensions for higher order.